Just a brief overview of the lecture. We're going to be talking about Moore's Law, how technology is finally reaching its physical limits, the basics of computing, what makes up a computer, quantum computing 101, quick primer into what quantum computing is, and how it can be useful for the machine learning and AI community. And finally, we're going to use an example of quantum computing versus classical computing to illustrate the potential advantages of quantum technology. So Moore's Law, since the 1960s, the power of machines have grown exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. The computer parts are approaching the size of a single atom, and to understand why this is a particular problem, we have to clear up some basics. So Moore's Law refers to the number of transistors on microchip and how it manages to double approximately every 2 years. So just last year we had chips like the AMD Ryzen 7 that had 5 billion transistors on its chip. And these chips are getting smaller and smaller, but we've managed to pack more and more transistors into it. A computer is made out of very simple components, each with a specific task. We have the memory unit that stores data, the arithmetic unit that processes it, and a control unit that issues the commands. A computer chip is made up of many different circuits, and each circuit is made up of modules that execute particular functions like addition and multiplication, and each module is made up of logic gates, and each logic gate is made up of transistors. A transistor is a switch inside a chip, and these transistors either let electrons through or not. They block them off, and because of this action of either letting it through and not letting it through, it can be classified as a binary state of either being on or off, and we call this a bit. So the bit can either be 1 if it's letting electrons through, or it could be 0 if it's not letting electrons through. Combination of these bits can be used to represent more complex information. For instance, transistors can be combined to create these logic gates. In this case, this is the AND gate. That still do very simple things. For example, here we have an AND gate that sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of many logic gates finally form meaningful modules, say for adding two numbers together. As we try to fit more and more transistors into smaller and smaller chips, our transistors are around 14 nanometers large, and that's, to put in comparison with an HIV molecule, it's a tenth of its size. And small objects will begin to have quantum physical behavior, and that's when things get weird. As objects become smaller than the size of an atom, in this case the electron, they start to have strange behavior. They can behave like particles, and they can also behave like waves. And here in the example on the left, here is an electron that's fenced in by iron atoms. And you can see that this electron that's been fenced in exhibits a wave-like pattern, showing its ripples going outwards. Similarly, when you do a double slit experiment using a light source, these photons, when passing through two small slits, exhibit additive and subtractive behaviors, like waves when captured on a screen. In a classical sense, a transistor either lets an electron through, and in this case many electrons in an electrical current through, or blocks their passage. And in the quantum picture, when you're talking about letting one single electron through, harnessing the power of quantum, these electrons behave like electrical waves, an electron wave. And when there's a wave involved, this additive and subtractive nature of the wave makes it so that there's a probability that the electron passes through. And this probability of passing through essentially means that electrons can often end up from one end of the transistor to the other in what's called quantum tunneling. And if this occurs, then you cannot have a subatomic transistor because you have no energy barrier that can actually record whether or not you've let it through. So there can be no bits that have been recorded. So in normal computers, we have bits as the smallest unit of information. But in quantum computers, we use qubits, which can be set to one of two values. A qubit can be any two-level quantum system, and what that means is it could either be a spin that's spin up or spin down, or it could be a magnetic field or a single photon. So all of these are quantum objects. And 0 and 1 are the system's possible states, just like the photon's horizontal and vertical polarization. But in a quantum world, a qubit doesn't actually just have to be either 0 or 1. It can actually be any proportion of both states at once. And this is called quantum superposition. And as soon as you test the value of an actual photon or an electron, it collapses into 0 or 1 when it's measured. As long as it's unobserved, a qubit is in a superposition of probabilities of 0 and 1, and you cannot predict which it'll be. But the instant you measure it, it's either one of those two. Superposition is a game changer in terms of what quantum computing brings to the table. In a classical computer, 4 bits means that you can have 2 to the power 4 combinations of data being stored and represented. And one combination must be represented at a time. However, in a quantum computer, 4 qubits can be all 16 combinations at the same time, and 20 qubits can store 1 million values simultaneously. Quantum entanglement is another unintuitive properties that qubits can have. An energy source could render 2 qubits entangled with one another. And this close connection makes it so that each qubit reacts to a change in the other state instantaneously without any regard for distance. This means that when you measure just one entangled qubit, you can also deduce properties of its partners without actually having to look. The difference between a classical circuit and a quantum circuit is that in the classical circuits, bits are the input values, and you have logic gates that manipulate these bits to also yield a result that is represented in bits. In a quantum circuit, a qubit in superposition is the representation of your input all at once, and you have quantum gates that then entangle these qubits to one another, harnessing the power of quantum entanglement to manipulate their probabilities of becoming zeros and ones. And your result is represented in a superposition all at once. And when you measure it, you get all of your solutions all at the same time. However, the most optimal solution, or the solution that you're looking for, is buried amongst all of this data. And there are a series of statistical algorithms that allow you to deduce which solution is most likely correct. In a case when a lot of data is involved, this particular strategy of finding everything out at once and then trying to use probabilities to deduce which is the most optimal solution is many times faster than what a classical computer could do, which is evaluate one solution at a time. And this is just an example to help understand how a question can be evaluated in a classical way and in a quantum way. So here we have Becky, Alice, and Chris looking to go from Toronto to Los Angeles in 2 vehicles. Becky and Alice are great friends, but neither of them actually want to be on a vehicle with Chris. So the idea is you want to maximize the number of friend pairs that share the same car and minimize the number of enemy pairs that share that same car. So to evaluate this, you can store this particular data and represent it with bits. If you take, for instance, taxi number 1 is 0 and taxi number 2 here in gray is 1, Each person has only two choices to be either one of those cars, so all the combinations can be represented in a total of 3 bits. Here in this case, we'll say Alice is A, Becky is B, and Chris is C, and they're all sharing the same vehicle. If you were to calculate the score of this particular pairing, it is that there's one friend pair and 2 enemy pairs in that car. So the score of this pairing is -1. If you represent all of these combinations and you put it in a table, you can see very quickly that there's 2 solutions that are the most optimal, and both of them involve Chris being in a car alone, and these yield scores of 1. So these are both the best solutions. You can see that this problem right now is fairly simple, but if you were to map all of these possible combinations out, the more people you have, the more cars that you have, the bigger this problem becomes to map out. And therefore, a classical computer will have difficulty in scaling in terms of these kind of problems. To put this in perspective, if you had 3 people, there'd be 8 possible configurations. 4, you'd have 16. But with an n number of people, you'd have 2 to the power of n configurations, which is the classical approach to this particular problem. You would have to calculate each one of those configurations. And if you have a really, really large number, it becomes impossible to solve these kind of problems with a regular computer. This is when quantum solutions give a scaling benefit. In a sense, classical solutions with 3 bits means that you can evaluate one of 8 configurations at a time, but a quantum computer with 3 qubits can represent all 8 configurations at the same time. So when you apply any sort of computation, in this case we're doing addition with these 3 qubits, you're computing all of those 8 configurations at the same time. So even with 100 people and 100 qubits being used, the number of operations that's required to solve the problem is only 1. For a quantum computer to solve this particular problem, all the solutions have to be represented with qubits in a superposition. There needs to be a quantum function that turns each potential solution into a score. In this case, this is the function that would count the number of friend pairs and enemy pairs that share the same car. Because you're getting all of these solutions at the same time with the quantum computers, there's going to be errors associated with it. It will also find these suboptimal solutions to your problems. But these errors will also become more prominent as the solution scales up with more and more qubits being involved. So in practice, you may want to run the same operation on a quantum computer dozens of times or even hundreds of times, and try to pick the best solution out of the ones that you're getting. And there are certain algorithms that go and evaluate this on the basis of probability and help you arrive at the best solution with quantum computers. In the case of database searches and even deciphering encryption, this process is much faster than actually evaluating all the possible solutions one at a time, like you would if you were to do it on a classical computer. That's the end of my primer on quantum computing. Don't fret if any of that was confusing. As the famous physicist Richard Feynman at the California Institute of Technology said, if you think you understand quantum mechanics, you don't actually understand quantum mechanics.